Let's now have a look at a question which is completely seemingly unrelated to antiderivatives. Let's have a look at the problem of finding areas of patches. Let's consider this area here. If I want to find this through a mathematical technique, how do I go about doing it? Well, this particular shape is a little bit complicated, but how about I chop out a section of it? Let's say I want to find the area given by this curve in here and this box, this area in here. Now this is something we can tackle mathematically. Let's have a go at sketching that as a function. Let's consider the patch of that area as bounded by a function y equals f of x in the region of the red box. And let me set the boundaries of that box by the limits x equals a and x equals b. How do we go about finding this area in here? So this shaded area, then how do we find this mathematically? One way to do this is to try and approximate it, and one way to approximate it might be to draw in a series of rectangles. So now I've got a bunch of rectangles. I could have a go at estimating the area underneath that curve. So I'd divide it into a bunch of strips. Each strip is approximately a rectangle, and an area of a rectangle I can find quite easily. Let me now label these strips. Let's say I've got n thin strips, then I start by labeling x1, x2, x3, x4, xn minus 2, xn minus 1, xn. And xn is equal to b and x0 equals a. Now, what's the width of each bin? If I take this bin here, let's call this width delta x. The width delta x is just going to be given by the total length b minus a over the number of strips. And the height of each bin is given by the function value at the strip point. So given this, I can now write down an approximate area for the formula. So the approximate area then, I'm going to write as A with n strips. So it's going to be f of x1 times delta x. What's that area correspond to? Well, that corresponds to this rectangle here at the height x1. Now add on f of x2 times delta x. This corresponds to this area at the height f of x2, and so on. We add up all of those. That's an approximation to what that area in grey is. Now what we're going to do is we're going to use our idea of infinitesimal limits to take the limit as our width shrinks to 0, our delta x shrinks to 0, as the number of bins tends to infinity. If I just keep slicing this up ever finer, I'm going to get a more and more accurate answer for the area of that shaded area. And in fact, we have that the area is equal to the limit as n tends to infinity of the sum over n bins of f of x times delta x. In forming this, I've actually used what's called the right-hand limit, in the sense that I've taken the value of the function in the interval from xi minus 1 to xi as xi. But actually, any function value in that interval is fine. And we denote that with a star here. And this means that it's any sample point in each interval. So if we just zoom into one of these, I can just choose any old point in there, xi star, with which to evaluate the function. And in the limit as n tends to infinity, it becomes less and less relevant which point I choose. So this could be xi, as I did in the diagram before, or it could be xi minus 1, which is known as the left point rule, or it could be a midpoint, or any other rule that you care to make up. Now, this special limit is called the integral of the function from a to b, and it has its own special notation, what's known as the Riemann sum formulation of the integral of a function. So it's got its own special notation. We see that we have in here this stretched s standing for sum over strips of infinitesimal widths, if you like. We have here a and b. These are called the limits of integration. This part in here, f of x, is called the integrand. And we note that this term evaluates to be a real number. So this we write as existing in R. It's not a function. And in fact, I can equally write this as the limit from a to b, the integral from a to b, of f of t dt. So the dt in here tells me what I'm integrating with respect to, and is actually a dummy variable in an integral like this. How do I go about evaluating an integral using a Riemann sum? Well, let's try an example. Let's find the integral from 0 to 2 of x cubed dx. Okay, so let's break it down. We need to find delta x and then a suitable place to evaluate the function. So delta x is b minus a over n. So let me write this as 2 minus 0 over n. Now let's figure out what the xi's are. So we start with x0. That starts at 0. x1 is x0 plus delta x, which is 2 over n. x2 is x1 plus delta x, so that equals 2 over n plus 2 over n, which is 4 over n, so on. So you see that xi is 2i over n. With this then, we see that if I just evaluate the function at the right hand point, so at x1 and x2 and so on, we just have 2i over n cubed times delta x, which is 2 over n. And this simplifies to. Now, the sum from 1 to n of I cubed, this can be evaluated as n into n plus 1 over 2, all squared. So the limit then becomes 2 to the 4 over 2 squared times n into n plus 1 over n squared, all squared, which then becomes just equal to 4. So this integral then evaluates to a real number as expected. And it's quite a faff to find it like that because you have to work out this infinite sum.